Okay, this is the Chapter 16 review. I'm going to start with 30, and I'll do through the last problem, which was 51. Okay, they gave you this chart listing concentrations and pHs, which is the weakest acid. For the weakest acid, I would look for the one with the highest pH, and in all concentrations you got acid 4, and that's got the highest pH comparing all three, all four. Okay, which one is your strongest? This one's going to simply be the lowest pH. So the lowest pH looks like acid number 2 in each circumstance. So acid 2. Okay. Now these are your equilibrium problems. I have a pH of 0.55 molar solution of hypobromous, HBRO. So the first thing is you have the dissociation of HBRO with water, forms hydronium plus BRO. Okay. The X is insignificant because let's see. We want the Ka. Okay. So it doesn't really matter about the X because we're going to know what X is. I know that the pH is 4.48, so the X is 3.31 times 10 to the negative fifth. So there's really no reason to use an X here. I would say 0.1234333, 0.1234333. That 33 is insignificant, so it's 0.55. Define your K, plug your values in. The value, like I said, was insignificant. The answer is 2.0 times 10 to the negative ninth. Okay. I do my problems a little differently than this. I would actually put the numbers in. If I knew the numbers, I wouldn't use an X. The Ka is 1.8 times 10 to the negative fifth. What's the pH? And it's acetic acid, so I have to look up and know, well, I have my Ka, 1.8 times 10 to the negative fifth. Now I'm looking for the X's. You put in your dissociation, you define your K, throw it in the ice box. You got 0.1 minus an insignificant X, because that K, if I go K divided by concentration and it's less than 10 to the negative third, which it is, it'd be 1.8 times 10 to the negative fifth divided by 0.1, which is 1.8 times 10 to the negative fourth, and that's less than 10 to the negative third. So the X can be disregarded compared to the 0.1. Keeps you from using the quadratic equation. Plug in your X's, solve for X 0.013, find a negative log. The answer is 2.87 positive. Hypochlorous acid, same thing. Make your equation. Now we want the percent ionization. To get percent ionization, you just have to find your H3O. So it's just like finding the pH. You're going to say the H3O divided by the total times 100. Okay, so plugging it in, I get a Ka of 3.8 times 10 to the negative fifth. I have X squared and 0.015, and the X is insignificant because that's a very small K. X ends up being 2.2 times 10 to the negative fifth divided by the total, 0.15. The answer is 0.14%. I reworked this problem on my version, and I'll tell you why. Originally, this problem has a very large K, 1.7 times 10 to the negative 2. To actually do this problem the way it originally was, you would have had to use the quadratic equation. So I replaced a stronger acid, sulfurous acid, with a weaker acid, carbonic. Okay, you have two K's for each H coming off. The first K, instead of being very large, 10 to the negative second, it's very small, 4.3 times 10 to the negative seventh. I set up my first dissociation. I can plug it in. The X is insignificant. This X in the original problem, actually, that was very significant, so you wouldn't get that answer. Solving for x equals, it's a different number than that, but you end up with your pH coming out to be 3.57, which I changed to D. Okay. As your concentration of weak acid decreases, the percent ionization increases. Okay. That's just something that you find in the reading in the book. There was a problem where we took an acid, and as we decreased the concentration, the percent ionization increased. This is the same concept. Consider this solution, 0.5 molar solution of nitrous acid. They showed the dissociation. Okay, how would the number of moles of HNO2 compare to the original solution? And this is if I diluted it. Well, dilution increases your percent ionization. You could view that as you're going to have more collisions of the acid with the water. So your percent ionization increases, and how it compares is it will be smaller. Okay. Let's see. I mix that with that. You're making actually it's a buffer. What species present in the lower concentration? Okay, I've mixed H2PO4 with HPO4, these two things. Okay, what's going to happen is you're going to get a lot of phosphoric acid. Because he's K's, this one's going to go more to the left. And so with both these going more to the left, it's going to lower that, shift it to the left. And your lowest concentration, if you look how small that Ka is going to be phosphate. Okay. This problem, we added two equations, we have two K's, so if you add equations, your K's multiply, so the answer is 2.5 times 10 to the negative fifth is C. And that's just, when you add equations, your K's multiply. We did that in class. Identify weak bases and strong bases. Methylamine, I would say that's like a derivative of ammonia. So that's definitely a weak base. Carbonate is a weak base, and KOH is a strong base. Anything with free hydroxide. Which correctly represents the reaction of a weak base in water? Here's your water, there's your base. The H would donate to make HA plus OH, so the answer to that's D. Which one represents a weak acid in water? Here's my weak acid, HA, here's my water. It would donate an H plus to the water to make H3O and acetate. Okay. These are just equilibrium problems. When I give you this test assessment on this, I'm not going to include any equilibrium problems. It's just going to be general theory. Okay. What's the value for Kb? What's different about this one, it's a base, so it's accepting the H. You have to have water in it. You could say BH plus OH, and knowing that this expression is now a Kb, and we're solving for OH, not H. So we plug in our numbers, x squared on top, 0.55, the x is insignificant. Okay, if you do that math right there, it's insignificant. Again, I wouldn't use the x's because you know the pH, 11.5. You can find out your concentration of OH is 0.00316. I would just put that number right into here. Plug it in squared minus divided by 0.55. The answer is 1.8 times 10 to the negative fifth D. Very similar problem. Now, if I look at this, That messes a lot of people up. I could just call that a base, B. Same thing, accepting an H. BH plus OH. So the conjugate of that is CH3, NH3. All I do is add an H for the conjugate, and it becomes a plus 1. Okay, that's what we're calling BH plus 1. I don't know the H concentration now, so I'm good to use an X. It's got a relatively small KB, kind of borderline. If I have x squared divided by 0.35, assuming that I don't have to use the quadratic, 4.4 times 10 to the fourth, your concentration is 0.0124. It actually is slightly significant. So if I was giving you a different sample, I would just pick something with a lower k. Take the pH, the negative log of that, it's 12.09. Probably if I use the quadratic, it's going to be off by a couple points, but close enough. Okay, which conjugate base is the strongest base? Okay, if I look from my smallest Ka, that'll be the largest Kb, because Ka times Kb equals 1 times 10 to the negative 14th. So the lower your Ka, the stronger your base, so the answer would be HC. The conjugate would be ClO negative 1. Okay. The Ka for that is at, what's my Kb? Ka times Kb equals 1 times 10 to the negative 14th, 2.0 times 10 to the negative 5th. Structure. Okay, which one forms the strongest acid? Okay, number 1, I'm looking for the one with the most electronegative, which would be S. Okay, once I get the S, the strongest one would have the most oxygens. Now, this is a weak acid. What would be stronger? That would be H2SO4. Okay. You want your most polarized acid is the answer for that. Which one's my strongest acid? The one with the most oxygens is the most polarized. They all have iodine in it. So HiO4. Okay. Which one is the strongest from below? Okay. If I look at this, I think I modified this problem on my sheet. These are all equally strong in water. HF is weak, HCl is weak, but in a non-polar solution, okay, in a differentiating solution, HI would be the strongest because I is the largest, so the H would be able to leave the easiest, okay? And then based on the strength, which one's the strongest? These are all binary acids. In this group, O is the most electronegative, the smallest, then S, then Se, so C fits. And a carboxylic acid, everyone should recognize as RCOOH. And we've been looking at that since the beginning of the year. All right, that's the packet. And what I'm going to do is put on a online multiple choice test for this, now that I've given you a review on it. And you can post any questions, and I'll try and open up a Zoom session before we do that.